Hi, welcome back to Organic Chemistry. In this section, we're going to start looking at functional groups that involve heteroatoms. Heteroatoms to an organic chemist are those things other than carbon and hydrogen. Pretty much, we're talking for us about oxygen-containing functional groups. We will see some nitrogen-containing functional groups as well. Could be others, but those are really the biggies for organic chemistry. And we're going to start out with alcohols. As I'm sure you know, an alcohol is something that has an OH group attached to a carbon. This is structurally very closely related to a water molecule. You've got the same oxygen with two lone pairs and two bonds, the same bent shape. Like water, alcohols are both hydrogen bond donors and hydrogen bond acceptors. A little bit of naming. You name alcohols by picking out the longest carbon-carbon chain and naming any branches off that carbon-carbon chain. But to denote that this is an alcohol, you change the suffix from ANE to OL. Well, actually, I guess you just change it. So what I mean by that, you take this first one, a 4-carbon chain is butane, but this is 1-butanol. Notice I have to say where the alcohol is, and it's got a methyl at position 3. In the second one, sorry, by the way, this is also known as 3-methylbutan, 1-ol. Those are both perfectly fine ways of naming it. This example is 3-methyl-2-butanol. Notice, by the way, that the OH takes precedence over the methyl in terms of the numbering, because I could number this as 1, 2, 3, 4. That puts the alcohol at position 2 and the methyl at 3, or 1, 2, 3, 4, which puts the methyl at 2 and the alcohol at 3. But the alcohol wins in terms of naming. And then 2-methyl-2-butanol for this last one. These are examples of primary, secondary, and tertiary alcohols, respectively. A primary alcohol is one in which the hydroxy is attached to a carbon that's got only one other carbon group attached, and therefore two hydrogens. A secondary alcohol, the hydroxy, is on a carbon that has two carbon groups attached, and therefore one implicit hydrogen. And a tertiary, the hydroxy is attached to a carbon that has 3 carbon groups attached. We'll use that terminology of primary, secondary, and tertiary a little bit when we're talking about alcohols. A couple of other naming things. First, just if you hear the term alcohol outside of organic chemistry, you are probably speaking specifically of ethanol. That is the compound that is found in beer, wine, liquor, etc. Another naming thing is that hydroxybenzene is commonly known as phenol. What are the properties of alcohols? The properties of alcohols are generally related to that hydrogen bonding group. Like water, these have generally high boiling points. If I compare dimethyl ether to ethanol, these two compounds are isomers of each other. Generally speaking, as molecular weight goes up, boiling point goes up. But here there's a huge difference, even though these have exactly the same molecular weight. Why? Because ethanols can involve in hydrogen bonding to each other, whereas dimethyl ethers cannot, because dimethyl ether has lone pairs, so it could act as a hydrogen bond hydrogen bond acceptor, but it can't act as a hydrogen bond donor, and therefore you can't have these things hydrogen bond to each other. Another property of alcohols is their solubility. The very small alcohols, like methanol, ethanol, and 1-propanol, are miscible with water. That is, they completely mix. I can go from 1% alcohol and 99% water to 99% alcohol and 1% water without ever having any sort of separation into two separate phases. On the other hand, other alcohols reach a saturation point, beyond which they won't dissolve anymore and they'll start forming a separate layer. But you'll notice that the longer the chain, the less soluble they are. So 1-butanol is saturated when it's 1.1 molar, but 1-pentanol, you can only get to 0.3 molar before you reach the point of saturation. 1-hexanol, 0.58, and 1-heptanol, 0.008. And finally, 1-octanol is immiscible. It doesn't dissolve in water at all. It forms two separate layers. just like some of the purely organic things that you've seen, like ether and dichloromethane, for instance, are two things that you've put in a separatory funnel in lab and seen them form two separate layers. Because we've got two different parts of an alcohol. There's the OH part and there's the alkane part. And the more the molecule looks like a hydroxy, the more it looks like water, the more it will mix with water. On the other hand, the more it looks like just a long carbon-carbon chain, the more it's going to behave like just hexane or something that doesn't dissolve in water at all. And so this really comes down to the balance between these two aspects of the alcohol. And the longer the carbon-carbon chain, the more the alcohol behaves just like just a straight alkane. Another property of alcohols is their acidity. They're similar in pKa to water. So you can deprotonate an alcohol to make an alkoxide. That's what we call a conjugate base of an alcohol. And for instance, cyclohexanol has a pKa of 16. Compare this to, this is pretty much very similar to the pKa of water. Now, there are some special cases. For instance, phenol has a much lower pKa. That means it's much easier to deprotonate. Why? Well, because in this case, my O- is the negative charge is stabilized by resonance, because I could bring these electrons here and push them all into the ring, for instance. And this is 10 to the 6th times, this is 1,000,000 times more acidic than a non-conjugated alcohol. Alcohols can be synthesized in a variety of ways, most of which are review to you. For instance, they can be made by substitution reactions from alkyl halides. They could be made by electrophilic addition to alkenes, by the addition of strong nucleophiles to ketones and aldehydes, by the hydrolysis of functionalities like esters, and by the opening of epoxides. We'll just go through a couple of these very quickly because you've seen them so many times. If I had a primary alkyl halide and I treated it with a strong nucleophile, such as a hydroxide, well, the hydroxide displaces the bromide and the product is an alcohol. If I had a tertiary leading group and a weak nucleophile, such as water, well, I would get a mixture of E1 and SN1 products, but if my nucleophile is water, after loss of a proton, my product is an alcohol. My substitution product is an alcohol. Also, alkene chemistry is something we've already spent a lot of time on. So I'll just remind you that you can make alcohols from alkenes by adding H and OH effectively in either a Markovnikov or anti-Markovnikov fashion, depending on which set of reagents you use. Nucleophilic addition, something that goes back to last semester, when in lab you made a Grignard agent. A Grignard agent behaves like a carbanion. If I have a methyl magnesium bromide, that behaves as if I had methyl anion. And that is a very strong nucleophile, and that methyl anion will add to a partially positive center, such as a ketone. If a strong nucleophile added to the carbonyl carbon, electrons get pushed up onto oxygen, you make an alkoxide, which upon protonation affords an alcohol. You don't just need a Grignard, lots of strong nucleophiles. Alkyl lithiums and alkyl magnesium halides are both essentially act as carbanions, but we also saw carbanions like the conjugate base of a terminal alkyne or the enolate ion. We'll spend more time on the enolate ion a little bit later on. Also, hydride ions, lithium aluminum hydride and sodium borohydride, are both effectively sources of H- as a nucleophile. And these also act as strong nucleophiles. Depending on what ketone or aldehyde I have, and what strong nucleophile I add, I can get any variety of alcohol that I wish. For instance, if I took a ketone and I added a Grignard to it, well, I've got a carbonyl with 2 carbon groups, and I add a third carbon group. That will give me alcohol. If I instead added a hydride agent to a ketone, well, I start with 2 carbon groups around my carbonyl, and I add a hydride, secondary alcohol. If I had an aldehyde, and I treated it with a Grignard, so I have a carbon and a hydrogen group around my carbonyl. If I add another carbon group, that'll give me, again, a secondary alcohol. And if I took an aldehyde and I treated it with lithium aluminum hydride, or sodium borohydride for that matter, primary alcohol. So notice, with a judicious choice of carbonyl containing starting material and nucleophile, I can get whichever alcohol I wish. For instance, let's say I wanted to make this alcohol. What is this? 3-hexanol. I would recognize, retrosynthetic analysis, I would recognize that either a ketone or aldehyde, if I were to add a third group, I would get this particular alcohol. And so it's all a question of, I could start with an aldehyde and add a carbon group, or I could start with a ketone and add a hydride group. So for instance, if I started with butanal and I added a 2-carbon Grignard, ethyl Grignard, I would get 3-hexanol. If I started with propanal and I added a 3-carbon piece, I would get the same alcohol. And if I started with 3-hexanone and I added a hydride agent, again, I would get to the same product. But what if I added my strong nucleophile, my Grignard or my lithium aluminum hydride, not to a ketone or aldehyde, but to another functional group that contains a CO double bond, for instance an ester? I find that this also gives alcohols. Now how does this happen? Well, first I want to recognize how the starting material relates to the product. We see that if I had a 3-carbon chain in the starting material, and I've got a 3-carbon chain with this oxygen in the product, those are probably related. These hydrogens, it turns out, comes from lithium aluminum hydride. Notice if I had methyl Grignard, I have 2 methyl groups that came from the methyl Grignard. So my nucleophile added 2 groups here, and this other hydrogen on the oxygen came from a H+, from an acid workup. We can do a variety of experiments to prove that. But let's see if you accept that those are how the pieces come in, how we can figure out the reaction mechanism. Well, I know that a strong nucleophile is going to want to add to a partially positive center, such as the carbon end of a CO bond. So let's add our Grignard. Electrons go up onto oxygen. But at this point, if I had a ketone or aldehyde, this would just stick around until such time as I protonate it. But if the electrons came down to reform a carbon-oxygen double bond, I could kick out an O-. And notice this would be relatively energetically neutral because I'm going from O- in this intermediate to kicking out an ethoxide, which would be an O-. But my product of that is a ketone. But that ketone is in the presence of more methyl Grignard because we've got a flask full of molecules. And so it's not like we only have 1 molecule of Grignard for every 1 molecule of ester, because this ketone is surrounded by more Grignards. And in fact, we know that Grignards react readily with ketones. In fact, they react more quickly with ketones than they do with esters. We'll come back to that point later. To make another oxyanion, another alkoxide, which upon protonation gives us an alcohol. Notice we brought in our strong nucleophile twice. First here to the ester CO double bond, but then after kicking out the O-, we have a ketone and we bring in another equivalent of our strong nucleophile. So we end up adding 2 equivalents of our strong nucleophile. Just as a little bit of an aside, we're going to come back and spend a lot of time on this in a subsequent unit. But this process of having, in our example, an ester, where I've got a CO double bond, and I'm going to treat the O-ethyl on that previous slide as just a leaving group. And I've got some strong nucleophile. A strong nucleophile can come in here Electrons go up onto oxygen, make an intermediate, electrons come back down and kick out a leaving group to make a substituted product. We're going to see this addition elimination process multiple times in days to come. But let's go back to our previous reaction. If I took an ester and a strong nucleophile, like lithium aluminum hydride or a Grignard agent, I would add 2 equivalents, and so I would end up making an alcohol. But notice, depending on if I use a hydride agent, I will make a primary alcohol. If I use a Grignard, I will make a tertiary alcohol. I can't make a secondary alcohol by this particular pathway. Other things to note, esters are not as reactive as ketones, so you can't stop halfway. But since esters are less reactive than ketones, the less sodium borohydride, which is less reactive than lithium aluminum hydride, doesn't react with esters. So if you had an ester and sodium borohydride, you'd get no reaction. An ester and lithium aluminum hydride, you'd get the addition of 2 hydrides and the loss of an ethoxide, and after protonation you'd get an alcohol, a primary alcohol specifically. You can also get alcohols from esters in another way, by hydrolysis. Hydrolysis means cleaving lysis with water, hydro. And if I took an ester and water, I would break it in half in such a way that I get a carboxylic acid and an alcohol. And the alcohol comes from this portion of the ester. So the water comes in, and the OH and the H came from water. The OH in the carboxylic acid and the H in the alcohol come from the water. How does this work mechanistically? Well, let's protonate our ester to make a carbocation intermediate, and that's positively charged center. A water molecule can come along and add. After loss of proton, we get an intermediate, which, if I'm still in the presence of acid, I could protonate any one of those 3 alcohols, any one of those 3 oxygens. If I protonated one of the OHs, well, I'd be back to the previous intermediate, but that's okay. As we'll come to in a bit, we'll see that this is a totally reversible process. But if I protonated the other oxygen, I'll make oxygen with 3 bonds. Let's break a bond. If I broke the OH, I'd be back to the previous intermediate, but if I broke the oxygen bond, I would make a new carbocation, which upon loss of proton gives us a carboxylic acid. But notice down here in the lower right corner, we gave up an alcohol. So in our balanced equation, we go from an ester plus water to a carboxylic acid plus an alcohol. Another functional group that can be hydrolyzed is the ketal and things related to the ketal. This is a ketal. A ketal is derived from a ketone. This is a hemiketal. It's kind of a halfway to a ketal. This is an acetal. An acetal is really the equivalent of a ketal, but it's derived from an aldehyde. And a hemiacetal the same way. If I took a ketal and I treated it with acid and water, I would get a ketone and I would get alcohol. 2 compounds, 2 equivalents of an alcohol. We'll get back to this in just a little bit. Finally, I can make alcohols from epoxides. But I'm not going to belabor this one at this point at all, because we'll come back to this when we talk about epoxides.
Alright, let's look at the reactions of alcohols. There are 3 main classes of reactions that alcohols will take part in. Many of these reactions are going to be reviewed. In many reactions, the alcohol acts as a nucleophile, and we'll see several examples of that. There are a few reactions in which alcohols are transformed into good leaving groups, and then you can go on to do things that involve good leaving groups, for instance, substitutions and eliminations. And then finally, we'll see the chromium oxidation reactions. First up, let's recognize that alcohols are like water. In their structure, they've got those lone pairs, and alcohols, just like water, are weak nucleophiles. On the other hand, you know that hydroxide, which is the conjugate base of water, is a strong nucleophile. If I took an alcohol and pulled off a hydrogen, I'd make an alkoxide, which is a strong nucleophile. So alcohols are weak nucleophiles, their conjugate bases are strong nucleophiles. What's some reactions that involve nucleophiles that we already know? This is all old news. Well, you know that a hydroxide does an SN2 reaction if I've got a primary alkyl halide, for instance. Well, an alkoxide also does an SN2 reaction. So I could take an alcohol, treat it with a base, sodium hydride is often used, and I will get this alkoxide as the conjugate base, and then if I add a primary alkyl halide, or other leaving group, an SN2 reaction will occur to make a new oxygen-carbon bond. This, by the way, is called the Williamson ether synthesis. You're making an ether. An ether is a functionality that involves two carbon groups attached to oxygen. Another reaction you saw water involved in way back last semester is the SN1 reaction. We know that when I treat a tertiary alkyl halide in a polar solvent with a weak nucleophile, like for instance water, you're going to get SN1 and E1. You're going to get a mixture of products. Well, if my weak nucleophile wasn't water but was an alcohol, in this case let's say methanol, that's my weak nucleophile and that adds to give an ether product. Again, also with some E1 product mixed in as well. Another reaction where we've seen alcohol used is additions to alkenes. For instance, I can treat an alkene with acid and water and do Markovnikov addition. Or I could, instead of using water, I could use an alcohol. So I could treat an alkene with acid and an alcohol and do the same Markovnikov addition. It's just my nucleophile in this case is the ethoxy. Formation of a carbocation at the more stable position, attacked by the ethanol to make this oxygen with 3 bonds and 1 lone pair, formal charge of +1. Well, we know what's going to happen in that case. Let's break a bond. If we break the OH bond, we form this ether product. Another reaction in which an alcohol behaves as a nucleophile, a weak nucleophile, is Fischer esterification. You might recall that if I treat an alcohol and a carboxylic acid with acid, I can get an ester plus water as a byproduct. Let's walk through the mechanism of this real quick. Pi bond reaches out, sorry, before I go on, the O carbon-carbon portion of the ester came from the alcohol. So this oxygen came from the alcohol. This oxygen is part of the water. Okay. So if I'm under acid catalyzed conditions, there's lots of things that have H plus acid wants electrons. There's lots of things. H plus wants electrons. There's lots of things that have electrons. Each of my oxygens has lone pairs. But let's use that pi bond, because it turns out that's going to be the most nucleophilic, the most Lewis basic portion. If this reaches out to make a bond, we get a carbocation. That wants electrons. If I've got alcohol around, well, that can add. I've got my old friend oxygen with 3 bonds. Let's break a bond. Of course, I could break the oxygen-carbon bond. That would lead back to this. I'm going to make the point in a moment that this is a reversible process. But if I lose the proton, I get this neutral intermediate. You might say it's neutral, that's not reactive, but there's more acid around. Acid wants electrons. All 3 of these oxygens have electrons. If this one picks up the hydrogen, we go back this way. But if either one of these, and because of symmetry it doesn't matter which, picks up a proton, we make, oh hey, if I break this bond, my leaving group is water. So let's break a bond and lose water, and then loss of a proton gives us our ester product. And notice water is the byproduct. Now I want to point out that this process is reversible. As I just went through, we can take a carboxylic acid and treat it with an alcohol under acid-catalyzed conditions and make an ester plus water. But we saw before, when we talked about the synthesis of alcohols, that you could take an ester and hydrolyze it. That is, an ester plus water makes an alcohol plus a carboxylic acid. And if you notice, each one of these steps, the steps for the forward process of acid plus alcohol to ester plus water, or ester plus water to make acid plus alcohol, if you go back and contrast the two mechanisms, you'll see that the intermediates are exactly the same. It's just the order in which they are happening, in a forward or reverse direction. So for instance, from this intermediate, I either lose this proton to make the ester, or I have water come in and add to make this intermediate. This is, like all reversible processes, this is driven by Le Chatelier's principle. If I have an excess of alcohol, I'll get pushed to the right. If I have an excess of water, I'll get pushed to the left. So I can go either way depending on my conditions. Another reversible reaction that involves an alcohol adding as a nucleophile. Oh, and I didn't make the point. And rather than going back on the previous slides, just look at the action of the alcohol. There's a point where there's a carbocation and an alcohol adds as weak nucleophile. But a similar reaction is the formation of ketals. Now here is a new reaction, so let's walk through it a little more slowly. If I take a ketone and I treat it with an excess of alcohol, in this case I show ethanol, under acid catalyzed conditions I will form a ketal functional group with water as the byproduct. We've also mentioned that if I add a ketal and I treat it with water under acid catalyzed conditions, I will form a ketone plus an alcohol. We mentioned this under the discussion of ways to make alcohols, and I said hydrolysis of various functionalities. Well, this is a reversible process. The forward and the reverse reactions here are in equilibrium with each other, and I can drive it one way or the other, again, by Le Chatelier's principle. So let's go through the mechanism of ketal formation. And ketal hydrolysis will just be the reverse. But if I have a ketone under acid catalyzed conditions, it can reach out to form the protonated form, which has a carbocation that needs electrons. Alcohols have electrons. An alcohol can act as a weak Lewis base and add to that carbocation position. Here's our old friend oxygen with 3 bonds. Let's break a bond. If I lose a proton, I get this species, which is called a hemiketal. A hemiketal is halfway to a ketal, halfway between a ketone and a ketal. But we're still under acid catalyzed conditions, so if we protonate, well, I can protonate either of the oxygens, but if it's the O-ethyl, I'd be going back to the previous intermediate. Again, this is a reversible process, but if I protonate the OH, I get an intermediate which has a great leaving group, water. If water leaves, we form a carbocation which can get attacked by a second equivalent of alcohol, and after loss of a proton, we get our product. Again, each of these steps is reversible. The mechanism for the forward process and the reverse process are identical. It's just the direction of the arrows that's changed. And let's see one last reaction in which an alcohol adds nucleophilically to an electrophilic center. And that's the formation of a tosylate. If I treat an alcohol with para-toluene sulfonyl chloride, that's this thing. Toluene, as you know, is methylbenzene. So this group is the para-toluene portion. It's para because the methyl here is opposite the sulfonyl chloride. This is often abbreviated as tosyl chloride or just TSCl. So here the TS means everything except the chlorine. If these two things are mixed in the presence of some weak base, such as a pyridine, we'll form a tosylate. This is a toluene sulfonate ester. So this kind of looks like an ester. An ester has a CO double bond OR group. This has an S with 2 double O's and then the OR group. So this is the sulfonate ester. But again, this is just often abbreviated as OTS, a tosylate. There are similar reactions that make things called mesylates and triflates, as shown down here, or that's methyl sulfonate ester and trifluoromethyl sulfonate esters. We're just going to focus on the tosylate, but the mesylate and triflate are really, for all intents and purposes, the same thing. Slightly different reactivities, and we can talk about why one might use one in one case and another in another, but really not of interest to us right now. We'll make the point with just the tosylate. All right. How does this work? Well, a sulfonyl chloride is a really reactive thing. We know a CO double bond is partially plus on the carbon. If I've got an S with two SO double bonds, each of those is a polarized pi bond. And so the sulfur is very electrophilic. And even very weak nucleophiles, like alcohols, can add to the sulfur. Push electrons up onto oxygen. And this is actually going to be one of the few times where I'm not going to break a bond around oxygen next. Because what I'm going to do is reform the SO double bond and kick out a chloride. And if we lose a proton, we get to our sulfonate ester, or our tosylate group, if you'd rather. Notice this is an addition elimination process. We'll see many additional elimination processes, especially when we talk about the reactions of carboxylic acid derivatives. Okay, but why is this interesting? Why would we make this tosylate thing in the first place? Well, let's just step aside and say paratoluene sulfonic acid, which is also known as tosic acid, is a very strong acid. It's probably one of the stronger of the organic acids, and it's really on par with things like HCl, HBr, H2SO4. Why? Because when you deprotonate it, you get this really resonance stabilized intermediate. Right? You can imagine drawing resonance forms, pushing this oxygen lone pair to sulfur and pushing electrons up onto either of these two oxygens. And the real thing is a weighted average that kind of shares the negative charge across all the oxygen atoms. Well, a tosylate is a great leading group for exactly the same reason. Right? It forms, when it leaves, a very stabilized anion. And tosylates do all of the things that good leading groups do. So any reaction that involves an alkyl halide, well, I guess not gradient formation. But when I say this, I mean really, when you talked about SN1, SN2, E1, E2, you pretty much always used halides as the leading groups. Tosylates do those same things. So for instance, if I had a primary tosylate and I treated it with a strong nucleophile, in this case at the bottom of the page, and the settled anion, we know that's going to do an SN2 process where the lone pair on carbon reaches around This is an example where an alcohol, an OH group, got turned into a better leaving group. And then in a subsequent reaction, that could go on and behave as a leaving group. But we've already seen in the past, in fact, in lab, you did this next reaction. Reactions where an alcohol is turned into a good leaving group and something happens, kind of all in the same pot. For instance, if I treated an alcohol with concentrated sulfuric or phosphoric acid, I would get an acid-catalyzed dehydration. That is, I would lose H and OH and I would form a pi bond. Well, how's that happen? Sulfuric acid is a very strong acid. Let's protonate the alcohol, so it's going to donate a proton to somebody. Oxygen's got those lone pairs. But if I form oxygen with 3 bonds, let's break a bond. If I break off of water, I make a nice stable molecule. I got a carbocation, loss of a proton, and that will make the alkene product. Now, interestingly, this is really an E1 process. If you notice this, a leaving group goes away to form a carbocation, and then a proton is pulled off of the adjacent position to make a pi bond. Way back when we first talked about SN1 and E1, we said they always go hand in hand. But there's a few cases where they don't, and this is one of them. Because the sulfonate, the sulfate, the conjugate base of sulfuric acid, it really doesn't want to act nucleophilically and add to that carbon to give what would be an SN1 type process. Instead, it really wants to pull off a proton instead to give the E1 product. On the other hand, if I used a different acid, if I use concentrated HCl, it turns out I get a different product. I get a substitution product. Well, let's see how this happens. We know that HCl is a strong acid, and so just like with sulfuric acid, we can protonate that alcohol and turn it into a good leaving group. If it leaves, making a carbocation intermediate, well, it turns out chloride doesn't want to do E1 mechanisms. A chloride ion will not pull off a proton from the adjacent position, and therefore it will rather add to give SN1 substitution product. So here again, we don't get a mix of SN1 and E1, we get really SN1 in this particular case. But what's happening as far as the alcohol goes? It's being turned into a good leaving group, water, which leaves in the process of the mechanism. There are other reactions that make alkyl halides, just like that last one made an alkyl chloride, and they similarly involve turning an alcohol into a good leaving group. If I treated an alcohol with PBr3 or PCl3, or, well, there is no stable PI3, but if I mix phosphorus and I2 in situ, that means in the flask, I can't pull down PI3 off the shelf because it wouldn't sit in a flask for long enough. But I can, inside the flask, mix phosphorus and I2, and I will make in this case, well, in that case I would make an iodide. But in each of these cases, I'll make an alkyl chloride. A fairly specific one, if I treat an alkyl with thionyl chloride, and that's SOCl2, the OH will get replaced by a chlorine. And this all of these reactions involve turning an alcohol into a better leaving group. How does it work? Well, if I take an alcohol and PBr3, the alcohol can add nucleophilically to phosphorus and kick out the bromide. This is doable because bromide is such a great leaving group, and because the phosphorus-bromine bond is relatively weak. We form this intermediate that's got oxygen with 3 bonds. Well, let's break a bond. But instead of something coming along and pulling off a proton, let's have that bromide really do an SN2 backside attack, kicking out this phosphorus piece to give our alkyl bromide product. Thionyl chloride goes by an interesting process. Here's the structure of thionyl chloride, and that S is very electrophilic. That sulfur-oxygen pi bond is a polar pi bond, and the sulfur end is partially positive. And if a nucleophile, even a weak nucleophile, reaches out to it, we can form a negatively charged intermediate, or an intermediate with a negative, that's not overall negatively charged, but with an O minus. And you know what, let's reform the the SO pi bond. But in the process, let's kick out a chloride. If that deprotonates, we get this thing that's kind of weird. It's a mixed, well, it's kind of a, well, scratch what I was about to say there. It's not really a mixed anhydride. It's just a very unstable species. And if that thing can actually fall apart all by itself, but if it does so, the oxygen, the O minus, can reach down to sulfur to form a sulfur-oxygen pi bond, kicking out chloride. But that chloride is being formed right next to a carbocation, and so we'll end up making an alkyl halide. And our byproduct here is SO2 and HCl. And SO2 is a gas, and it'll bubble out of solution. And that'll really help push this reaction forward. I'm not going to belabor it, but this thionyl chloride formation of an alkyl halide gives retention of configuration. You might think about when the electrophile is formed, that is, after the oxygen-carbon bond is broken, where is the chloride? It turns out it's on one particular side of the carbocation, and so you end up forming that nucleophilic, that SN1 product. There are some differences. If you had a primary alcohol, it behaves slightly differently. If you threw in a pyridine additive, you'd have a very similar reaction, but in that case we get a backside attack and we get inversion of configuration. Our third and final reaction mode of alcohols is alcohols can be oxidized by various oxidizing agents. And to talk about oxidation, we really have to step back a bit and talk about oxidation states. Here are 5 molecules that involve carbon, but it turns out carbon has different what are called oxidation states in each case. Oxidation state is really sort of an accounting tool to help us figure out sort of which element lays best claim to the electrons. And reactions that involve oxidation and reduction involve changing sort of the ownership of electrons, if you will. Oxidation is losing electrons formally, and reduction is gaining them. So this is often an abbreviation for redox reactions or oxidation reduction reactions that says oil rig. Oxidation is losing, reduction is gaining. But how can we account for who is gaining and losing electrons? Well, that's oxidation states. You'll learn more in Chem 4 about oxidation states, and you'll spend a lot more time on redox chemistry. But we're going to look just at organic species, so we can take a pretty simplistic approach in this class. But let's introduce oxidation states. There are a few rules to figure out oxidation states. The first rule is that hydrogen usually has an oxidation number of +1. So in each of these cases, the hydrogen has an oxidation number of +1. And oxygen usually has an oxidation number of -2 in compounds, not in its elemental O2 state. And the carbon, on the other hand, it comes down to the context. For a neutral molecule, the sum of oxidation numbers must be 0. You'll notice in methane, since each of the hydrogens has an atomic number, well, they do have an atomic number of 1, but that's not my point, has an oxidation number of +1. If for the total of all of the oxidation numbers for all 5 atoms to add up to 0, the carbon has to have a value of -4. In the next case, methanol, since I've got 4 hydrogens, each of which has a +1, an oxygen which has a -2, the carbon must have a -2. And so on and so forth, through the third, fourth, and fifth molecules shown. Notice carbon doesn't have anything set in stone. It can change from one oxidation value to the next. And if I move from left to right along this pattern, notice I've got increasing oxidation values, or oxidation numbers, oxidation states, whatever. And this is called oxidation, when you've got an increasing oxidation state. The opposite direction would be called reduction. And we're going to focus in on the central 3 molecules here. We're going to say if I go from an alcohol to a ketone or aldehyde, that's oxidation. And if I go even further to a carboxylic acid, that's even more oxidation. How do we do these processes? Well, there are many reagents, truth be told, but we'll focus on 2 of them. And they're both chromium-based. PCC, which is pyridinium chlorochromate, is a combination of chromium trioxide, HCl, and pyridine. But really, the active species is the chromium trioxide. The HCl and pyridine, this is a base, this is an acid, they're really there to move protons back and forth. There's chromic acid, which is shown here in magenta as chromium H2CrO4, and it's got a structure really similar to H2SO4. Chromic acid is not something that you tend to keep on the shelf in lab. It's really nasty stuff. And so what you would do instead is keep solid sodium perchromate, Na2Cr2O7, on the shelf. It's really easy to work with solids. Liquids, if they spill, they get all over. Cleaning them up is an issue. A solid, if it spills, you just sweep it up. It's very easy. Solids are easy to measure out. Liquids, well, you can measure them out using grad cylinders, measure them by volume, but a little bit harder. So sodium perchromate is a lot easier to work with than pure chromic acid. But sodium perchromate is not chromic acid. But if you mix it with sulfuric acid, and quite frankly, sulfuric acid is around it's something that's commonly around labs. Well, if those two things are mixed in aqueous conditions, you will form chromic acid. This is generally done in situ. That is, instead of making up chromic acid and having it sit around, or having a bottle on the shelf of chromic acid, in the flask that you want to react, you mix sodium perchromate and sulfuric acid. I am just going to say chromic acid, but you will see other people write a combination of sodium perchromate and sulfuric acid, or you might see that in some texts. Now, these two molecules, in this case, the oxidizing agent is the H2CrO4. In the PCC, the oxidizing agent is CrO3. If you compare and contrast these two species, what do you notice? Well, it's water is the difference. Chromium trioxide, if you added water to it, you'd get chromic acid. Right? That's the H2O is the difference between those two structures. And the PCC conditions are done under very rigorously dry conditions. Because, I'm sorry, I had to pause and I lost my thought here. The difference between CrO3 and H2CrO4 is H2O. And if I was to take chromium trioxide and mix it with water, I would get chromic acid. So the PCC conditions, kind of like the Grignard reaction, involve fairly careful conditions where you exclude excess water. The chromic acid conditions, on the other hand, are wet. There is inherently excess water around. That'll come into play when we talk about some of the reactions. Let's look at those reactions. If I mix PCC and a primary alcohol, a reaction would occur. And here's how this mechanism works. Chromium trioxide reacts with acid, and remember the PCC conditions included HCl, an acid, and pyridine, a base. So protons are kind of coming on and coming off. But chromium trioxide, if it gets protonated, gives a positively charged chromium. And just as an aside, notice, okay, this may look weird because it's got a different element that we haven't used before. But mechanistically, there's nothing surprising to us about a pi bond reaching out to make a bond to hydrogen and making a positively charged center in the process. Okay, we got chromium, it wants electrons. Oxygen has electrons. So oxygen can reach out, make a bond to chromium. After loss of a proton, you get this thing called a chromate ester. But it turns out this chromium is a great leaving group. And in fact, it's really easy to pull off a hydrogen. And remember, pyridine, which is a base, is involved in the PCC conditions. If pyridine comes along and pulls off a hydrogen, electrons will go in and kick out chromium as a byproduct, and form a CO pi bond. By the way, in this process, chromium is being reduced from chromium 6 to chromium not chromium 6, from chromium 12 to chromium 10. So the chromium is being reduced, and what's being oxidized? The carbon. Because remember we said that species that were alcohols, if I was able to transform them into a species that was a ketone or aldehyde, that is an oxidation step. A key to understanding this process is the fact that these steps are all reversible. But this one is irreversible. And if I've got a series of reversible steps, but any one step is irreversible, well, anytime the molecule's like this, yeah, it could go like that, but if it does this, well, it's stuck like that. And what we're going to find is that that's going to lead to product. So back and forth and back and forth, back and forth and back and forth. But then an irreversible E2 elimination gives us our product. If I had a secondary alcohol, exactly the same process would happen. Notice this slide is identical to the previous slide. I just put another R group here. And since that R group was not part of the mechanism, there's no difference between this example and the primary alcohol I generically referred to on the previous page. A series of reversible steps forming this thing that's called a chromate ester, and then an irreversible process, E2 elimination process, that affords a CO double bond. What if I had a tertiary alcohol? You know, it turns out a tertiary alcohol can do many of the same things as a primary and secondary. It's still got those lone pairs, and it can add, making a chromate ester. But if you recall in those previous examples, they all involve deprotonation of the next position over in an E2 elimination to form a pi bond. This one doesn't have a hydrogen on the next position over, so such a hydrogen cannot be deprotonated, and therefore, even though this chromate ester is formed in reversible steps, it can also fall apart again. And that's ultimately what it does. So in this case, yeah, stuff happens, but there's no net change. There's no overall transformation. And so we would say that no reaction occurs. So let's summarize this. Notice with each of these cases, if I treat an alcohol of any stripe with PCC, a series of equilibria will happen to make the chromate ester. So there's this series of reversible steps making the chromate ester. But if there's a hydrogen on this position, as there is in the primary and secondary alcohol case, well, an E2 elimination will happen to make an oxidized product. But if we can't do that irreversible E2 elimination step, we will see no net reaction. So this is the summary of PCC oxidation. If I have a primary alcohol, I will oxidize and make a product which, well, since I had a carbon, a hydrogen, and a hydrogen, and I did an E2 elimination involving a hydrogen, I have a carbon group and a hydrogen. That's an aldehyde on my CO double bond. That's an aldehyde. If I started with a secondary alcohol, after I lose this proton, I've got two carbon groups and a CO double bond. That's a ketone. In this bottom case, if I had a tertiary alcohol, back and forth and back and forth, these are all in equilibrium. But this case doesn't have a hydrogen on this position. And so we can't do that E2 elimination step. And so this will ultimately fall back apart again and afford your starting materials. In other words, there's no net reaction. Now, this is just as an aside, this is a great time to remind you of a point I've tried to make over and over again. Even the most complex mechanisms you'll ever see, and this is probably the most complex mechanism you'll ever see, certainly in Chem 2, Chem 3. Even the most complex mechanisms come down to just new combinations of the same fundamental steps. And so I just want to walk through this many-step mechanism and make that point. What do we have here? First, pi bond reaches out to H+, positively charged center, and then a nucleophile comes along. Right? That's just electrophilic addition to a pi bond. Sure, in this instance, it's a chromium-oxygen pi bond, and most of the examples we saw before were carbon-carbon pi bonds. But mechanistically, pi bond reaching out to electrophile, positively charged intermediate, and then a nucleophile comes along is nothing new. What happens in the next couple of steps? oh, we just pulled off a proton and we protonated something else. That's just acid-base stuff. That's proton transfers. Okay, what happens in the next couple of steps? Water goes away, we get a positive charge on chromium, and then we lose a proton from the next position over to make a pi bond. Hey, wait, leading group going away, positively charged intermediate, and then loss of a proton to make a double bond. That's just an E1 elimination. Again, it's involving different elements than we did before when we talked about like alkyl halides in E1 elimination, but mechanistically the arrow pushing is the same. This next step, well, that's just an E2 elimination, right? Loss of a proton, kicking out a leaving group, forming a pi bond, all in one step. That's just an E2 elimination. These next couple of steps are electrophilic addition again, right? Pi bond reaches out to H+, water comes along. Some proton transfer, another electrophilic addition, more proton transfers, more E1 eliminations, and then finally another E2 elimination. So this many-step mechanism involves just the same things that you learned back in Chem 2. Additions, eliminations, this one doesn't involve any substitutions, and proton transfers. And really, those four, counting substitutions, which isn't in this example, form the bulk of organic mechanisms. Alright, back to the reactions though. We talked about the reaction of an alcohol, a primary alcohol with chromic acid. What about a secondary alcohol? Well, we could draw the exact same mechanisms, so I'm not going to walk through them in detail. But where chromic acid gets together with the alcohol in a series of reversible steps to make a chromate ester, and this irreversible E2 elimination gives a CO double bond. And then we can do a series of reversible steps with water to form a hydrate, and then with chromic acid to form another chromate ester. But now we don't have any hydrogen at this position, so we can't do the irreversible E2 elimination step. So while these things form, they also fall apart, because these are reversible processes. And so eventually we just get our ketone out. Since there's no hydrogen at that point, we can't oxidize twice. And so we just stop after the first oxidation. I'm not saying nothing happens here, I'm just saying we see no net change after this point. That is, when we observe our products at the end, we're going to observe the ketone. What about a tertiary alcohol? Chromic acid and an alcohol can get together to make a chromate ester, but if I had a tertiary alcohol, just like with PCC, there's no hydrogen here, so there's no irreversible E2 elimination, and therefore this step, these things, while they can happen in a reversible process, well, they can also unhappen by that same process. And eventually it will fall apart and we'll get the tertiary alcohol back. And so depending on primary, secondary, tertiary alcohol, we'll get a carboxylic acid, a ketone, or we'll just stay with our original alcohol. Let's sum up the oxidation of alcohols altogether. If I had a tertiary alcohol, it doesn't matter which reagent I use, I get no net reaction. If I have a secondary alcohol, it doesn't matter which of these two reagents I use, they both give the same product. They both give ketone. The difference comes in primary alcohols. If I had a primary alcohol and treated it with PCC, I would get an aldehyde with chromic acid, and I would get a carboxylic acid. Alright, and that's alcohol chemistry. Alcohols do essentially three things, as I mentioned. We saw several reactions where, in a key mechanistic step, oxygen lone pair reached out to some other position, so the alcohol acted as a nucleophile, or the conjugate base of an alcohol acted as a strong nucleophile. We saw several reactions that involved transformation of the alcohol into a good leaving group, and then taking part in some process such as substitution or elimination that involve leaving groups leaving. And then finally, on this slide, the oxidation reactions. All right, that's it for alcohols. Thanks for listening, and I look forward to talking to you again about other heteroatom containing functional groups. Thanks.